Hello everyone, this is video 2 of the chapter 2 of the lecture notes, Fundamentals of Cryptography. So here we are discussing the general framework and the basic notions to deal with cryptosystems in general. In this video we're going to introduce a very important distinction, namely the one between what we call symmetric cryptosystems and what we call public key cryptosystems. This is really a crucial distinction that changed how we think of cryptography in modern days. And as you will see, it's a very, very simple distinction to understand. Okay, so to start, let us just remember again what is a crypto system, and perhaps in a more succinct way that we did in the first video. So if I want to tell you a crypto system, I need two data, right? The first data that you need to give me is the choice of message units. Okay, so you need to tell me if this crypto system that we are using is breaking the text into letters, into digrams, pairs of letters, trigrams, and so on. And the second thing that you need to tell me is the choice of the enciphering and deciphering transformations, right? Of enciphering and deciphering transformations. Okay, so any crypto system is the data of these two items. Transformations. So if we use the same notation as in the previous video, the message units, the plain message units are P, the ciphered message units are C. So the enciphering transformation goes from P to C. This is the enciphering transformation, and it depends on some parameters that we call the enciphering key. And then we have the inverse function that goes from the ciphered to the plain message units, which we call the deciphering key, and deciphering transformation, which depends on some parameters, called the deciphering key. Okay, good. So given this, we can understand very easily the distinction of, on the one hand, public key cryptosystems, symmetric, I guess I should put on this side, symmetric cryptosystems on the one hand, and on the other hand, public key cryptosystems. Okay, so let us start defining what is a symmetric cryptosystem. Okay, so as we have any crypto system, we start with the knowledge of the enciphering transformation here. Okay, so let us put this in another color, perhaps in blue, the enciphering transformation here. Enciphering transformation, and we ask the following question. Suppose you know the enciphering transformation, so you have the knowledge of enciphering. Is it the case, yes or no, that with the knowledge of the enciphering transformation, you can automatically deduce the knowledge of the deciphering transformation? Of the deciphering transformation. If the answer is yes to this question, then you're dealing with what we call symmetric cryptosystems, right? So as soon as I give you the enciphering transformation, you can deduce on your own the deciphering transformation, okay? So the data of one is equivalent to the data of the other. That's why I put them in the same color. An example of this was the shift transformation that we discussed in the previous video, right? An example, if the enciphering transformation is shift plus 3, then the deciphering transformation is shift minus 3. And I have not given you any new information by telling you how to decipher, because you can deduce this on your own. Okay? So that's what a symmetric crypto system is. And until the 1970s, it was thought that all crypto systems behaved in this way, that as soon as you knew how to encipher a message, you automatically knew how to decipher the message. This, however, has changed, and in public key crypto systems, it just happens to be the case that the knowledge of the enciphering transformation, is not equivalent to the knowledge of the deciphering transformation. So you can know how to encipher a message, and it's not because you know how to encipher a message that you automatically know how to decipher a message, okay? So if I have P and C here, it's not because you have this blue information that you will know how to compute the reverse arrow. So I have to draw this in another color, okay, to insist in the fact that these two are different informations. And this was in fact discovered in 1975 by three very important people for cryptography: Diffie, Hellman, and Merkel. Okay, so you may wonder, how is this possible? How is it possible that there exist bijections in which you know how to compute it in one direction, and yet it doesn't give you the information on how to do it on the other direction? So this is possible because of a concept that we call a trapdoor function. Possible because of trapdoor functions. And I'm going to give you an example, an explicit and very simple example in a second. Trapdoor functions. Okay, so trapdoor is something that, you know, a trapdoor is something that you can move in one direction very easily, and yet you cannot move in the opposite direction very easily. Okay, so more precisely, it would be a bijection that you can compute very easily, but the inverse is very hard. Okay, so easy to compute in one direction, easy to compute in one direction, compute in one direction, but hard in the other direction, in the opposite direction. Okay, so this existence of trapdoor functions is what allows us to do a modern cryptography. And let me give you an example of a trapdoor function, which is going to be used to develop one of the cryptosystems, the RSA cryptosystem that we are going to discuss in chapter 3. This example is multiplying two factors, multiplying versus factorizing. So multiplying is very easy, and factorizing is very hard. And what I mean here, to be more precise, is multiplying prime numbers between them is very easy, and yet having the result and factorizing into prime numbers is very hard. So let me just show you an explicit example of this. I've taken here the Wikipedia page of RSA numbers, which are numbers that are actually used in cryptography, and I'm just going to show you with one example here. So for example, here you have a huge prime number, and we're just going to ask the computer to compute the product. This number times, let's take the second one, huge prime number, and let's see, these are quite big prime numbers, right? Can it do the computation? So let us just ask Wolfram Alpha, and you see it took less than a second for the computer to find the result. Okay, so that's pretty easy. Now we can ask the opposite. Let's just take the result here, and let's ask the same website to, okay, you have the number, so now factor the number into prime numbers. Let's see, it takes some time, it understands what we want to do, and however, standard computation time exceeded. So the computer does not have the computational power to do this, okay? So this is a very explicit example where it's very easy to do this operation in one direction, and yet in the other it's not, okay? So for example, I could publicly say the result of the multiplication of these prime numbers, and yet probably no one here among us would be able to find the factorization of the two prime numbers that I have chosen, okay? So that's an example. The last thing that I want to discuss in this video is, and it's very important, is why are public key cryptosystems so important? public key cryptosystems so important? So important. Okay, this is a very important question, right? And I told you that the invention of the discovery of public key cryptosystems really changed the way we think about cryptography. So let me just continue our comparison between what we have on the one hand side, symmetric cryptosystems, and on the other hand, public key cryptosystems. So why are they so important? Suppose you have two people, right, that are communicating, A and B. Here, we have A and B that are communicating between them, right? And they use some crypto system and they need some some enciphering key and a deciphering key, right? First thing is that this EAB and DAB must be secret, right? They must be known only to E, A, and B, because as soon as anyone, the adversary, the enemy, knows how to encipher the message, it automatically knows how to decipher the message. So all the content of the messages between A and B become accessible to any enemy that knows either the enciphering key or the deciphering key, okay? However, if we have this, the same situation in the public key crypto system between A and B, well, we can say here we have a different matter. Here we can say we have EA, a way of sending messages to EA. Here, okay, a way of sending messages to B, EB, and these two can be public. Right? Why is this? Because if you know how to encipher, well, you can just send the message that is ciphered to A or to B. But since this does not allow you to decipher the message, the content of the message is safe, right? The only thing that needs to be secret is how to decipher the message. So A needs to keep secret its deciphering key, and B needs to keep secret its deciphering key. This needs to be secret here. Secret, right? Okay, so this changes quite a lot, this way of thinking. It's no longer about pairs of people, but about how to send to A or to B. And why is this such a big change? Let us just look in a second what happens if we have 5 people that are communicating between them. Okay, if we have 5 people, let's suppose we have them here, A, B, C, D, and E, right? 5 people are communicating. In the symmetric crypto system, C, D, and E. Well, what needs to be the case is that these two, they have their way of communicating, right? They decided to use shift +3 and shift -3 to decipher. That's how A and B are working. But A and C are working in a different way. That is secret and only known to A and C, so they have decided shift +17, for example. And there's also one way of communicating between these two, and we have, in fact, all of these ways of communicating, right? Every pair has its distinctive way of communicating, right? So if you count in total for each of these here, okay, I'm not going to write them all because it will take a long time, but here we have for each pair here, we're having a pair of keys, right? Okay, so if you count in total, we have here how many? 1, 2, 3, 4, 6, 10. 10 pairs of keys. To make all the ciphering communication between 5 people. If we have exactly the same scenario here, between these 5 people, A, B, C, D, and E, the situation is much more simple. Why? Because you can have here, in the public space, the ciphering keys, EA, EB, EC, EE, and ED. This is known to everyone. This is public. And secret, DA, DB, DC, DD, and DE. So in total, we just need 5 pairs of keys. So you see that when we are doing public key cryptosystems, we are reducing dramatically how many keys we are using to cipher. Imagine when we are doing this with billions of people using WhatsApp. If WhatsApp was using a ciphering cryptosystem that was symmetric, well, the number of keys would be exploding, exponential, whereas it's not in the case of the public key cryptosystem. That's why we can use this in WhatsApp, okay? So just to finish, here is the summary, right, of the advantages and disadvantages of symmetric cryptosystems versus public key cryptosystems. So the drawbacks of symmetric cryptosystems we have already discussed, which are mirrored by the advantages of public key cryptosystems. The only thing that is an advantage for symmetric cryptosystems that we have not discussed is that in fact they are much more simpler in their structure. So in terms of computational power, if you want to cipher a very big amount of data, well, with the symmetric cryptosystems, it will just take a bit less time, actually, much less time than if you were working with public key cryptosystems. But if the data is very sensitive, well, you have to use public key cryptosystems because they are much more secure, okay? So this is the end of video 2, and in the next video, we are going to see one example of not so sophisticated, but fairly sophisticated symmetric cryptosystem.